Hi there, it's Wendy again. Today is April Fool's Day, so there's that. This is the note catcher for probability, determining whether it's independent or dependent. And so we're going to be working on how can you tell. I feel like this is a lot of common sense, so I don't want you to overthink these. I feel like these are very much common sense. And then we'll talk about specifically how can you use a formula to figure out the answer. So let's look at A and just use common sense. So a person pulls a red marble out of a bag that has five blue and 7 red. And they do not replace it. They do not put it back. So I take a marble out and it's red, and I look at it and I see that it's red. And originally there were 5 blue and 7 red. Well, then I'm going to pull out another red. So is the probability of pulling out the second red dependent on pulling out the first? Well, I didn't put it back. So now when I pull out the second red, I only had 6 reds to pull from, but I still had all 5 blue. So it definitely does actually change my probability, because once I pulled that first red marble out, the number of marbles, the number of red marbles, it all changes, and therefore the probability changes. So that definitely does depend on pulling that first red one out. All right, so a person flips a coin and notes that it comes up heads. Then a person rolls a standard 6-sided die and notes that it comes up a number less than 3. Is the probability that the number came up less than 3 dependent on getting ahead when flipping the coin? Well, that one should be crazy obvious. Of course not. No, you can't. If you flip a coin and then you roll a dice, obviously whatever you got on that coin has no impact whatsoever on what you're about to roll on that die. So that is no, they are completely unrelated. All right, so let's keep going. The idea of independence is one that's pretty normal. It's kind of common sense, like I was telling you, but we do have an actual test to see whether something is dependent or independent, whether it depends on what you just did. All right, so let's look at example 2. The spinner below is spun one time and the outcome is noted. Okay, so we have this spinner, and I know you can see some of these answers, but the spinner spins, and it says that let E be if you get an even number, let P be if you get a prime number, and L means it's a number less than 5. All right, so the probability of getting an even number. Okay, again, this is easy. So it's 1, 2, 3, 4. There are 4 even numbers out of a total of 8. So the probability you're going to get an even number is 4 out of 8, or 1/2. All right, so now they want to know the probability of getting an even given that the outcome was prime. So we can only look at prime numbers. So 2, 3, 5, and 7 are prime. Out of those, only 2 is even. So that's the only even number. So 1 option there. Out of a total of 1, 2, 3, 4 numbers that were prime. So the probability that you would get an even number if you assumed that it had to be prime would be 1 out of 4. Okay, now let's look at this one. What's the probability that you would get an even number if you know the number had to be less than 5, given that the number had to be less than 5? Okay, so less than 5 and looking for even. So there are 2 even numbers less than 5 out of 4 numbers total that are less than 5. So 2 are even out of 4 numbers less than 5. So 2 out of 4 gives us 1/2. Okay? So then the question becomes, which event does E depend on, P or L? How can you tell, and what would be a reasonable test? All right, well, look at what happened here. When we just cared about getting an even number on the entire spinner, we had a probability of getting it. It was 1 out of 2. But when we wanted an even number that was dependent on it being prime, our probability was totally different from the original probability that was just looking at E. And then finally, when we had to make it E or even, but it also had to be less than 5, we were back at our same original percentage that we had, our same probability that we had when we were just looking at E. So we can look at it and tell that since our probabilities are different here and here, that E does depend on P. That is a dependent relationship because our probability was different. Whereas E does not depend on L or being less than 5. Even being even has nothing to do with being less than 5 because our probability was exactly the same as when we just cared that it was even. So if the probabilities are different, probability of E versus the probability of E given P, those are different, so there's a dependence there. But the probability of E, when you compare it to the probability of E given L, those have the same probability, so there's no dependence there. Okay? All right, so let's go to the next page. All right, so here we have two events, and what we're saying is basically when you put a second event on there and they are independent, it doesn't matter because your probability is the same as just getting the first event, no matter what that event is, okay? All right, so let's look at the next setup. All right, so here is example 3. A survey of 57 sixth graders was done to determine which subject was their favorite, and they're sorted by their gender. So they want us to find out that based on the data in this table, was the preference for math dependent upon whether they were male or female? All right, so let's see. So here's what we do, and I know you're seeing all the answers at once, but let's look at what we did. The probability that they liked math was simply a total of 18 out of 57. 18 people liked math out of 57. It was their favorite subject. So that's about 32%. But if you just looked at the females compared to the total, they had the number of females who liked math was 8 out of a total of 30 females. So the percentage of females, if we're only looking at females that liked math as their favorite subject, was 0.27. Whereas if we're looking at the number of males, the ones who were male and liked math, so 10 out of the total number of males, which is 27, when you divide that, you get 0.37. So look at all of our percentages are different. So the probabilities do vary based on whether it's a male or a female responding. So therefore, liking math, according to this data, does seem to depend on gender because all of those numbers were different. So now they want us to do the same thing, and I want to keep this chart in the picture. All right, so they want us to do the same thing for social studies. All right, so let's look. Look what happens with social studies. If I look at the total, just people who like social studies, no matter if they're male or female. So we go over here, and we have 19 people that chose social studies as their favorite out of 57. So 19 out of 57, when you divide, you get 0.33. Well, let's look at social studies, but based on whether they're female. All right, so we're going to go to female. Females who had the favorite subject of social studies was 10 out of a total of 30 females, or 0.33. Well, let's look at males that liked social studies, given that they're a male. So 9 liked social studies out of a total of 27, or 0.33. So look at that. All of our probabilities are identical. And so it looks like, according to this data, that liking social studies does not depend on the gender because those probabilities are all equal. All right, so there's just this easy little test to decide whether something is dependent on another event or whether the events are independent. And this is the product rule. All right, so this is the product test for independence. Basically, two events are completely independent if, when you find out the probability for A and B, the intersection of A and B, if it equals A times B, okay? So if A and B together, if the probability of those having overlapped, the overlap of A and B is equal to the probability of A times the probability of B, then they're independent. So let's test that with our very last problem. So we're going to use this product test to see if these are independent. The probability that a person is left-handed is 12%. The probability they have brown eyes is 42%. The probability that they have brown eyes and they're left-handed is 2%. So is it independent? Well, let's use our formula. So the probability that they have brown eyes and they're left-handed is 2%. The probability that they're left-handed is 12, and the probability they have brown eyes is 42. So we just plugged those in. I converted them to decimals. And 0.02, when you multiply these, you get 0.0504. And in fact, those are not equal. So we can put a not equal to sign there. So therefore, because they're not equal, they are not independent. They're not completely independent. Okay? All right. I want you to use this to have as a guide for your work time. I want you to make sure that you do at least the first page on your work time, which is numbers 1 through 3 today. And if you have any time whatsoever, if you're not finishing late in the day, then I definitely want you to try all 7. The more you do, the better you'll get, the easier the test will seem. But if you are struggling to finish all of your work, then at least do the first page, which is 1 through 3, and submit those on Google Classroom. I'll talk to you soon. Bye-bye.